Okay, so I'm going to upload my weight loss data. Where do I have this? In my documents. Here's our class. Go to today's class. Okay, here's my paired T data. That's what I call the data file, paired T data. And so we'll open that up. And so we have two sets of before and after. I actually do have data has column names. Yeah, so there's before and after column headers for both of these. And you can see they're kind of similar. I actually have the exact same befores for the, remember I said I made up this data just to get examples that highlighted what I wanted to do. So the befores are actually the exact same in both of these, but the afters are different. So like this first person in the first weight loss program, they actually gained like 14 pounds. And the second one, they lost 4 pounds. And here, this person lost like 30 something pounds. And in the second version, they lost 3 pounds. So there's not that many in the sample, only 25. But the befores are exactly the same. The afters are different. So I'm going to run 95% confidence interval for each of these 4 columns, just so we can get an idea of what the numbers are like. So we'll do stat, basic statistics, one sample T. We're just doing one column at a time here. One or more samples, one in each column. I wonder if I can do all 4 at the same time. That'd be cool. One or more samples. This is one or more samples, so we should be okay. 95% confidence interval. Why don't we do a histogram? May as well. And we'll hit OK and see what we get. All right, so as you can see, the two befores are identical. They both have a mean of 235, standard deviation of 66, and they both have the same confidence interval, 207 to 262, because the data is exactly the same in those two. Our first after has a mean of 229. The second after has a mean of 230, just a little bit higher. They're pretty similar. Their confidence intervals are different. The confidence interval is a bit wider for the first after than it is for the second after. So we have graphs for all of these. So that's what the before graphs look like. They're just sort of all over the place. And then the after happens to look like a bit of a bell curve, and this after is more spread out. It goes from like 140 up to 355. This after is similar, but it's sort of piled more in the center. Okay, so the afters are very different between the two afters. All right, so we have the exact same befores, and the two afters have almost the same mean. So in the mean, they both dropped like 5 or 6 pounds. So the before, like the afters are pretty similar in terms of their mean, but their standard deviations are kind of different, and how they're kind of spread out is different. So the confidence intervals look a little bit different. All right, let's run the two sample t-test comparing the groups. So this is not acknowledging any connection between the two groups. So each sample has its own column. We'll do the before and after first version. And that is the hypothesis test I want to run. And do we want a graph? No, we don't want the graph. Okay, so we'll hit OK, see what we get. All right, so the null hypothesis was that the mean weight in the first group, the before group, and the mean weight in the second group, the after group, are the same. And it looks like our p-value is 0.75. So as far as we know, the means are the same. I mean, look at this. Like the two groups, their means are only 5 apart. Their standard deviations are huge. They're like 60. So like since the weights are spread out from like the hundreds up to the 300s and the means are only 5 apart, it certainly seems reasonable that in a sample of 25, one extra high number or low number could be changed, and those means could be out the same. So as far as we know, these means are equal. Let's do the same thing for our second group. We'll change this before to the different before. this after to the different after. Okay, so will we find any difference here? Well, I'm thinking we probably aren't going to, because again, the means are only different by about 5, and the standard deviation is massive compared to that. So it wouldn't be that unusual to think that like adding one more person to this group could easily pull this mean up by 5, and then the means would be the same. So, and again, a high p-value of 0.8. But as we know, like it doesn't really make sense to compare like the fact that like in this second group, like all of these people are going down in weight. Okay, so like everybody, if you look through, like I set it up so that in the second group, everybody is losing weight. And it doesn't really make sense to lump together the mean of everyone in the first group and then just compare that to the mean of everyone in the second group, because then you're comparing these people that are like 350 pounds to these people that are like 170 or 119. You know, what's important is like how much each individual's weight changed, and that might not be the case in all of the tests we run, but this experiment is specifically set up for each person generates 2 numbers. So let's do the paired t-test, which doesn't just look at everybody here and compare it to everybody here. Instead, it looks at how much each person changed, and it understands that there's a paired set of numbers for each person, and the groups are not independent. So basic statistics, paired t. Each sample has its own column. We'll do before and after. Okay. So estimation for the paired difference. Okay, so before we just looked at the means of 235 and 229. Well, the important thing is that how much is the mean change? So on average, there's a difference of 6. And standard deviation is still quite a bit bigger than that. So we're still getting a p-value, which is bigger than 0. So as I mentioned, some of these people gained weight, some of these people lost weight, so it makes sense, I suppose, that we don't know if there's a statistically significant effect for this weight loss program. But I specifically set up the second group of data so that every single person lost weight, just a little bit. So in the first group, some people gained a lot, some people lost a lot, and then it sort of all balanced out so that we didn't know if the weight loss program did anything. But in the second set of data, everybody lost just a little bit. So on average, they lost 4.7, but everybody lost, like the standard deviation is very small. Everybody lost about the same amount of weight. And so here, the p-value comes out very small because like unnaturally small, because it is actually unnatural data. Because when the standard deviation is big compared to the mean, then you could think like, well, maybe the mean would actually be 0 with a little bit of luck. But here, the standard deviation is small compared to the mean. You know, everybody is really like right around 4, 5, 6. And there's nobody in zeros or the negatives. So you start to think like, okay, like I actually have a real pattern here that I can be confident represents like a real difference. Okay, so the regular 2-sample t-test didn't capture any of that. The fact that this first weight loss program didn't look like it was helping people. And you can, if you look deeper into the numbers, some people gain weight, some people lose weight. And you can't really tell if it's helping. But the second set, like everybody lost right around 4 or 5 pounds. And that is a statistically significant difference. All right, so we'll do this again for the exam data, which is actually real data, not stuff that I made up.